Okay, so this will be Chapter 7, Lesson 3. In this chapter we've been talking about the periodic table, and more specifically in the first two lessons about the trends on the periodic table. So we saw that the periodic table is arranged in a way to reveal a lot of physical and chemical trends in the elements, which gives support to the fact that we've arranged the elements correctly and we understand them, to a good degree. Today we'll talk about metals, the trend of metals. So let's define what metals are. In general, a metallic substance will be shiny or lustrous. So here you see an example. This is good old gold and a little bit of copper here, and both of these are both shiny and lustrous in their pure form. Metals are also malleable and ductile. This means they can be shaped. In fact, malleable just means it can be hammered into thin sheets like this gold leaf is, and that's why in the olden days people actually covered things with gold. You actually don't need a lot of gold to cover something, some sort of wooden statue completely with gold, a little bit of gold, because gold can be hammered out very thinly. Ductile means it can be strung out into essentially a wire. Today this is used for wire, and for that reason it's used in wires because metals are good conductors of both heat and electricity. Metals have very low heat capacities and they conduct electricity well, and metals then form cations. So metals will always lose electrons when undergoing a chemical reaction. And you can actually see the metallic trend. You'll notice that on the periodic table the nonmetals are toward the right. The periodic table's up here, and as you go down, you can see as you go, say, from nitrogen to phosphorus to arsenic to antimony down to bismuth. Eventually you get into the metallic trend. Maybe it's easier to see with the carbon group. Carbon's a nonmetal, silicon is a semimetal, germanium, and then you get down to tin and lead. Lead is definitely a metal, definitely metallic. So you can see the metallic trend as you go down, increasing. Similar thing happens as you go left, and you can see it here in the P block as you go from sulfur to phosphorus to silicon, and then you get to aluminum, which is also a full metal. In fact, aluminum is used very often in wiring. So you could think of, in a way, francium as being the most metallic, the really metallic metal of them all. But in general, this is the character on the periodic table. So we're going to talk about some reactions relating to this metallic trend on the periodic table. The first one we will introduce to you, or we'll first say that metal oxides, this is a compound of oxygen and the metal, are always basic. So the reaction that we'll actually deal with shows an oxide of metal, in this case sodium oxide, reacting with water in a synthesis reaction to form the metal hydroxide. Essentially, you can think of water essentially just combining with the oxide formula, and if you combine two oxygens here and two hydrogens, you'll actually get two sodium hydroxides. So because metallic oxides form bases, as we've learned in Chapter 5, react with acids to form salt and water, and that's exactly what you see here. This is magnesium oxide, which is a base anytime you put it into water, and because acids are aqueous, that means they contain water. So essentially you got yourself a metallic oxide being placed in water, which becomes a hydroxide. So here the intermediate step you can think of is magnesium hydroxide. And then the reaction between magnesium hydroxide and hydrochloric acid is well known. It's a double replacement acid-base neutralization reaction, forming magnesium chloride and good old H2O. We're actually going to try an example of this. So let's go ahead and try an example where we want to write the balanced equation for the reaction of aluminum oxide with water. So let's first write aluminum oxide. Recall that anytime you're writing compounds, you have to, if they're ionic, you have to be able to balance the compound, the charges of the compound. So we know that aluminum, for example, has to be balanced with oxygen. I think we'll do this on the next page. Let's go ahead and flip and do this on the next page. Yeah, we have a clear page for this. So we got ourselves. We're gonna go for the details here. So aluminum, which has a +3 charge, with oxygen, which has a -2 charge. So we need 2 aluminums for 3 oxygens. So our aluminum oxide is written as Al2O3. This will be reacting with water, and then the product, metallic oxides, form metal hydroxides. So then we'll have to do the same thing on this side. We have to balance aluminum, which still has a +3 charge, with hydroxide, which you recall has a -1 charge. This means we need 3 hydroxides for every aluminum, and we get ourselves AlOH3. Lastly, let's go ahead and balance the equation. We have 2 aluminums on the left, let's stick 2 on the right. That gives us 6 hydrogens. We have 3 here times 2. So let's go ahead and put a 3 in front of here. And that gives us 3 oxygens on the left, 3 oxygens on the left, and we're good. Now if you want to include the state symbols in here and try to write the net ionic equation for this, let's go ahead and this is aluminum oxide. Now metallic oxides by themselves will always be solids, because really any ionic compound is a solid. And then on this side, obviously, aluminum hydroxide, because we've placed it into water, is aqueous. So because nothing will cancel out on the left side, and this will be split up, you can say that your net ionic equation, which I don't think the web assignment requires net ionic equations, but if you were to write them, you will simply split up aluminum hydroxide here. So the picture would look like this. Aluminum oxide plus water provides aluminum +3 and 3 OH minus. This would be your net ionic equation, essentially. But I think WebAssign requires just the molecular equation, so this is actually what we're looking for here. Alright, nonmetals. We'll say a few things about nonmetals then. They are much more diverse in their properties and behavior than metals. And what you have is the nonmetals will always gain electrons, or they tend to gain electrons, because nonmetals are close to the noble gases, and in order to reach a noble gas configuration, they will require more electrons, whereas metals have to lose electrons to acquire that noble gas configuration. So here is an example. Here's a metal with a nonmetal giving you a salt. Aluminum with bromine giving you aluminum bromide. This is a classical synthesis reaction. So a good number of the reactions in this chapter will actually be synthesis reactions, and most of them will be between elements. So let's define a similar thing like we did with metals. We said metallic oxides are basic, and non-metallic oxides then are acidic. So what we have here, a famous non-metal oxide, is actually carbon dioxide. If you place carbon dioxide in water, what you get, if you combine the water formula, go ahead and put 2 H's and an oxygen on this formula, you get yourself this substance here. This is carbonic acid and carbonic acid. And this is actually what creates that little the fizz and the bite that you get. The fizz in the soda that you drink comes from the carbon dioxide gas itself, but the little bite sting that you get on your tongue for that pleasant sensation is actually from the acid that forms. And a similar thing happens with sulfur dioxide, except much more devastating to the environment. Is plants that give this off will react with rainwater and create sulfurous acid. This is a weak acid. Nonetheless, you can still eat away at statues and actually acidify the soil and change the ecology of the place that it sits next to, essentially. So, nonmetal oxides are acidic. So one way to remember, these will all be oxyacids that are formed. And a good way to remember, or a good way to guess which acid is going to be formed, because we know that there are two forms, for example, of phosphorus-based oxyacids. It could be based on the phosphate ion, which this gives us phosphoric acid, or it could be based on the phosphite ion. This gives us phosphorus acid. And you may not know just off the bat from the original substance what kind of acid would be formed. Sometimes it's not as logical as we've seen previously, where you simply add the water formula. We know that from the phosphorus oxide you'll get some sort of phosphate type acid, but exactly which one, there are two possibilities. To know exactly which one, we can actually take a look at the oxidation number, what we learned in chapter 4. So if you pull phosphorus apart here, what you'll find is that phosphorus has a specific charge. So if you take a look here, we have 10 oxygen. Remember, each oxygen is a -2, so we get -20 on this side. We have 4 phosphorus, so this side must be +20 because everything is 0. It's a neutral substance. And so the 4 phosphorus must be +20, which means each phosphorus must be +5. So here we get a charge of +5. Oxidation number, rather, of +5. If we do a similar analysis to the phosphorus here, or to the phosphorus and phosphate, what we'll see, let's get rid of the, so it's a little easier to work with and see here. So if you do a similar, that little guy is out. If you do a similar analysis, you got 3 hydrogens, each was +1, so that's +3. You got 4 oxygen, each is -2, so that's -8. The whole thing is 0, and so we know that phosphorus must be +5. So notice the two oxidation numbers match up, and we get ourselves, we know that we formed the right acid. And that's in some of the more difficult cases. That's what you'll have to do. And really your acids will be based on the polyatomic that you are aware of. It's essentially the polyatomics that we learned. Just base the acid off of it. The way to do that is if you find out the charge of your polyatomic and then place that many hydrogens in there. So notice that told us we have to have 3 hydrogens because each hydrogen is a +1 is the idea. And since we said nonmetal oxides are acidic, this means they will react with bases, again, to form salt and water. So we're going to actually do a reaction like this. Write the balanced chemical equation for the reaction of sulfur dioxide with aqueous sodium hydroxide. So let's go ahead and get to it here. So first of all, let's go ahead and write sulfur dioxide. And then we're going to react that with sodium hydroxide. So in essence, the sodium hydroxide is aqueous, which means there is water in the sodium hydroxide. And as soon as sulfur dioxide hits the water, it becomes an acid. Now let's think about what kind of acid it will become. So really you're thinking about putting the water formula into sulfur dioxide. In this case, it'll actually work really well. You could just put the formulas on top of each other to get yourself H2SO3, and this is sulfurous acid. So these combine together to give you sulfurous acid. Eventually, you don't have this anymore. You have yourself this substance here, your acid. So then we can think of this as a standard double replacement reaction. So now we can think about the hydrogen and the sodium swapping places, as we've seen before, and your two products then that result are a sodium sulfite, that's Na2SO3, Na2 because we had 2 hydrogens, since each sulfite was a -2 charge, and the other substance is HOH, or good old H2O. And that does it. In order to balance the equation, let's go ahead and put a 2 in front for the sodium. Let's go ahead and put a 2. Let's see, actually for the oxygens we are good. And this is actually our balanced equation. Not too difficult. If you think of your nonmetal oxide as the acid, and then write that acid out, it'll be easier this way. So this is the equation. And we're not going to bother with net ionic equation in these cases, but if you would like state symbols, we can put those in. Sodium sulfite is actually going to be aqueous in this case, since we've thrown it into water. Sulfur dioxide is a gas. If you're not aware of which ones are aqueous, which are gases, then we can give you some clues. We can speak a little bit more about in the class. I think we'll stop there just for the first lesson, and this will conclude there, lesson 3 of chapter 7.